Yeah.
Can somebody check the thing on the camera? Is it catching my,
It's easy.
it sees me?
Yeah, it's right there, or you're just right at the edge of it.
Yeah.
The edge moving like this?
Yeah, you're
Or
just
my
on-
head?
No, yeah, your whole body, you're just at the edge.
Okay.
That way.
Hey,
Good morning.
how are you? Careful
Good,
there.
how are you?
Okay. So about, is it still got me? Okay, so I can get that right here. The problem, does it cut my head off there?
No, you're good.
She went to Greece that same day. I saw her. I swear I have tried it. Yeah, I know, she took it out. I was like, girl, I wish I was here somewhere. It's weird. It's just, I have to scrub more. Scrub this off. I tried, like it's just,
Right. Careful with the cord there.
No, you're not.
All right, well, I got 10 o'clock, so we'll go ahead and get started. I'll just refresh everybody a little bit on what we're talking about. So, exam one. Exam one, I've provided you a copy of the periodic table. I've provided you your zip grade form. When you get to class, I'll tell you how to fill out the zip grade form. You won't need a calculator. You're allowed your model kit and you're allowed your handwritten notes. 25 questions plus one bonus. So each question is worth 4 points. The bonus is also worth 4 points. So in theory, you can get greater than 100% on the exam. We're going to cover the introductory material that we gave on the first day of class, all the way through the first half of chapter 5. And on the exam, I went as far as carbocation stability. We didn't get to carbocation rearrangement at all or anything like that, so I stopped on the exam before we got there. So that's what the exam looks like. So, the exam's situated where I've given you plenty of room to work on the exam. You're more than welcome to work, right on the exam all you want. And I've actually put some spaces on there where I say show work here, which is my way of saying don't do this in your head. But the exam is plenty of white space, plenty of area for you to work whatever you need to work on. And so I will be quiet now and answer any questions that you all have. Yeah.
Okay, I have 2 questions, because I was going through the textbook last night, taking some extra notes.
Yep.
And so my first question is, I remember that you said there's some stuff I had to memorize, and I'm okay with that. But there's also some other stuff, what was it? Like the strength of the weak acids and the strong acids, like how it goes from strong acid, weak base, and I don't know, like that chart. Do we have to memorize that chart?
No.
No? Okay. Just making sure.
No. You need to have a feel for what charts tell you. You need to know generally what a strong acid is, what a weak acid is, what a strong base is, what a weak base is. But on this exam, am I going to ask you to give me the pKa of any of the acids? No.
Okay. And then my second question is, there's also some other stuff like the textbook that we never went over in lecture, I guess. Would we be tested on that?
If it is in the reading assignment, it is fair game.
Okay.
I'm not saying whether it is or it isn't.
Yeah.
I'm just saying it's fair game. So the curriculum is a mixture of what I assign you to read and what we go over in class. I've covered quite a bit of what's in
Yes.
lecture. I may not have had a slide entirely devoted to some of it, but
Yeah.
there's some of it that I assume, it's pretty standard and easy. But Yeah, if it's in the reading, it's fair game. What else?
I got a question from the homework, but I'm not 100%, I can't really remember how it worked. It said something like true and false, I think in maybe chapter 3.
Okay.
It said, it asked, I think it said, confirmations are not isomers, constitutional isomers.
Okay, that's right. So a conformation is what the shape of the molecule is as a result of rotation around carbon-carbon single bonds, right? So one of the examples was the Newman projection, right? So we've got our back carbon and what's attached to it. We've got our front carbon and what's attached to it. And I'm just going to do this. And we can rotate around that carbon-carbon bond, right? And so if you rotate around that carbon-carbon bond, you might have a conformation that looks like this. Those are not constitutional isomers of one another.
Right.
Okay, all we're doing is rotating around a carbon-carbon single bond. A constitutional isomer is when we actually connect the atoms differently. So this, of course, is butane, right? But I could also have that, those are constitutional isomers of one another, right? So I've got 1, 2, 3, 4 carbons connected in a row, and here I've only got 1, 2, 3, and I've swapped the positions. But this is C4, 6, 7, 8, 9, 10, right? 9 and 10. So they have the same molecular formula, but they're connected differently. So those are constitutional isomers of one another. These are just a molecule rotating around its bond, but it's still connected. The atoms are still connected exactly the same way here and here.
Right. So, but on those two C4H10s, they're both named differently, right?
Oh, absolutely. Yeah, how would we name this one? What's the longest chain?
Butane.
Yeah, so it's just butane, right?
Right.
What's the longest chain here?
3.
Which is
The propane.
propane, right? So this is a propane parent, and then it is
1 or 2 methyl.
by definition, you can't have one methyl propane because then it becomes butane.
Right.
Right?
And the only thing that really changes with constitutional isomers is the,
Well, a lot changes with constant. They're not the same molecule.
right, but they still have the same molecular weight and stuff.
They have the same molecular weight, they have the same molecular formula, but this and this have different melting points, different boiling
Right, yeah, that's,
points.
what's the word for that?
Physical properties.
Physical properties.
Yeah, they have different physical, they can have different physical properties.
Right, okay. That's what
Okay, I understand where the 2 comes from, but remind me why it's propane. Is it because it's 3?
Yep.
It's because it was 1?
So there's our longest chain, right?
Okay, so 1, 2, 3, propane. Okay.
Don't be afraid to write and draw. I mean, really, circling the parent chain takes care of it. So, this is a multiple choice test. So you do need to use some good multiple choice test taking skills, right? Which is, if I gave you this, whatever, and let's say I gave you this and asked you to pick the name, circling this can eliminate a lot of stuff, right? Because you just determined that it's propane. So anything that doesn't list propane has to be wrong, and you can that's just not even right.
Unless you do all 4 answers with propane.
Yeah.
Well, that's possible, but I mean, how many ways can I name propane? I mean, it's only got 3 carbons, right? So, but if you couldn't determine that, then that's fine too. But it's easy to go through and eliminate first. If you determine something is a hexane parent, and I've got heptane and pentane, you just cross those out and don't even think about them anymore. You know what the parent is. you have to be confident that you know what the parent is and you correct, you know, I might have picked one that might be a common mistake.
I have a couple of homework questions, so I'm not sure, like, should I ask them like right now or should I wait after class and then?
You can ask.
Okay, well, for 414, in our books, I didn't understand B at all. It says, do you want to see the question? I took a screenshot.
You said 414?
Yeah. So- Then I did part A, but I didn't do part B. It just confused me.
Okay. So it's talking about this molecule allene. And we really haven't talked about these dashed and solid wedges yet.
So like, this is a question, like what she was saying, like we haven't really covered that in class, so I didn't understand it when I was reading. Would that come on the exam?
It could be a fair game question. I may not ask you something that involves this nomenclature about a solid wedge and a dashed wedge. But I could give you something like this and maybe ask you to tell me what the hybridization of the atoms are.
Okay, it wasn't, so the question also asked, other than the hybridization, that part we did cover, so that part was fairly okay. But B part was like, their orientation in space is different. Why?
Okay, you tell me.
I don't know.
No, you do. I know you do. Why are they different in space? So,
Is it like to do with like their stabilities and stuff? But it was like, because one side was like this, and then the other side was like this. So
okay, all right. So let's start by, let's first, and that was a two-part question, right? So the first thing you want to do is identify the hybridization. What are the hybridizations of each one of these carbon atoms?
SP2,
Okay.
SP for the second one, and SP2 for the third one.
So what does it mean to be sp2 and sp? An sp2 hybridized carbon atom, right, has sp2 hybridized orbitals and one p orbital that's not hybridized. But an sp has its sp orbitals, but it also has two remaining p orbitals, right? And those p orbitals can't be in the same space, right? So it gets a little hard to draw. But what you'll see is that this carbon atom in the middle that's sp hybridized will have a bond to these two carbons, right? I think we can all agree with that. But there's going to be on this a p orbital that's in the plane of the board. And let's just call it p, let's call this one py. Remember, there are three coordinates on a Cartesian coordinate diagram, right? So we can put a p orbital in the y, x, or z planes, right? So we have this. And each one of these carbon atoms also has a p orbital that is unhybridized, right? So let's just pick on this one. And so you end up overlap and making that second bond, right? And I'm drawing kind of four. So if this orbital is in the plane of the board, where's the other p orbital on this carbon?
Outside of the board?
It's outside of the board. That's hard for me to draw. But imagine that it's coming out of the board, half of it, and the other half is going behind the plane of the board. So it has to overlap with a p orbital on this one that's also to make that second bond. And so I've got one that's bound in the plane of the board, and I've got one that's bound perpendicular to that, right? 90 degrees. And so that's why these things are twisted, if you will. This stuff is coming out of the plane of the board for these because the p orbital is in the plane of the board. But since the p orbital here is coming in and out of the plane of the board, these have to be in the plane of the board.
So is it to avoid colliding?
Well, it certainly does do that, but it just has to be with the fact that the p orbitals are in one plane and in the other one they're in the other plane. And that's what allows the bonding to occur, and when you do that, you end up with your groups coming out of the plane of the board here and in the plane of the board here.
Could you say that in a sentence?
Um,
Like, how would we answer that question? Because like sometimes I can understand what you're saying, but it's like I don't know how to say that.
Okay. It all has to do, again, with where the p orbitals are. Okay, so once you know where the p orbitals are, then you know what has to happen to the other groups that are attached. If I have this p orbital in the plane of the board, these things can't also occupy that same space. They can't be in the plane of the board. Well, if they're not in the plane of the board, then they have to be outside the plane of the board. Here, the p orbital is not in the plane of the board. So the only other place for these to be is in the plane of the board. Does that make sense?
So,
So something along those lines would get you right. But it has to do with the fact that you end up with a pi bond between these two p orbitals and a pi bond between these two p orbitals, and they're 90 degrees to one another.
so the p orbitals don't overlap?
This orbital and this orbital do, and this orbital and this orbital do.
So the adjacent p orbitals don't overlap?
Yes, that's right. That's right.
Okay,
That's right.
that makes sense.
Now, since we haven't done the dashes and the solid wedges yet, probably I'm not going to focus on any of that type of B-type question. It would probably be more of the A-type question. What's the hybridization? We'll talk about this, I believe it's in chapter 6, where we start talking about some stereochemistry, which is my favorite topic. What else?
So if there's like a double one, so on 438, most of them are like EC, most of them are E. But if there's a double bond and it's like near a cycloalkane, how can you determine if it's high or low if it's like a cycloalkane?
Okay. So you're wanting to know, how do you determine priority? All right, so let's just take a double bond. Now, finish telling me what your question is.
It's like, I'll show you. So it's kind of like, because there's like a double bond here and then there's a cycloalkane.
Oh. So yours is on the beta carotene. I'm just going to put R there. I mean, it goes on forever. Right? So your question is, how do you determine the E or Z of that double bond?
Yeah, the one that's like by the cycloalkane.
This one?
It would
This
be-
one?
Yeah, that one.
Well, no, this
It's
one.
like- It's on this side, so I was trying to determine, but if
Okay.
it's like all connected.
All right, well, let's look at it. So we got to look at this carbon and this carbon, right? And we got to ask ourselves what's attached, right? All right. So let's start with the bottom one. I've got a CH3 and I've got a CH2 that's connected to a C. Which one of these is higher priority, this one or this one? This is a carbon and this is a carbon. I can't make a decision just on the first atom, right? Well, what's attached to this carbon?
Hydrogen.
3 hydrogens. So if you want to, you can just put in the 3 hydrogens, right? Just in parentheses. Well, what's attached to this carbon?
Another carbon.
Another carbon and
Hy-
2 hydrogens. So which one is higher priority?
Carbon.
This one, right? So I want to say this is high, this is low. Okay, so we've made that determination. Now I've got to look at this carbon atom, right? It's attached to a carbon atom and it's attached to a carbon atom. I can't make a decision, right? What's attached to this carbon atom? Another carbon, and another carbon. What's attached to this carbon atom? A carbon, and a hydrogen. Which one of those is the highest priority?
So on the left.
This is high. This is low. Right, so when I look at my, it's what? For that particular carbon-carbon double bond, yes.
Could you do the one next to it?
Yeah, we can do the same thing, right? So, let me erase all of that. So what do? We look at the carbon atoms, right? And ask ourselves what's attached. Well, I'm going to go ahead and draw it in. I've got hydrogens, right? So I've got a hydrogen here and I've got a carbon. So this is going to be low. This is going to be high. That's easy to do, right? This is a carbon. This is a hydrogen. So this is low. This is high. And when I look down that, the highs are on opposite sides. So it's
E.
E. That's right. So that's an E. Double bond.
Are the hydrogens going to be there first, or we just have to know that they're there?
Oh, maybe, maybe not.
Okay.
What's the rule of a hydrocarbon when we're drawing these bond line or bond angle structures? We don't have to draw the hydrogens in there attached to carbon. We know that carbon has 4 bonds, and we know if we have 3 bonds to other carbons that one of those bonds have, because we know it has to have 4, right?
Right.
One of them has to be the hydrogen. So I know when I look at this that that's a CH3, that's a CH2, that's a CH2, and that's a CH3.
Okay.
So I could draw it like this. I could draw it or I could draw it like that. You need to be able to go between both.
Because you could give us that, and then we have to draw from that point. Like,
I mean,
okay,
it's possible.
okay.
Yep. What else?
Can you do something about drawing a line structure with, based off of the condensed formula or the molecular formula?
It would be fair game for me to give you something like say I gave you something like that and asked you to pick the bond line drawing for that. That would be fair.
So how would you go about doing that? That one doesn't have any methyls or ethyls or anything, any substituents, right?
Does it?
I don't think so.
Well, if I draw it out, I've got a CH3, which is just going to be a dot, right? Or an end of the line. Then I got 3 CH2s, so 1, 2, 3. Then I've got a CH and 2 CH3s. So when I draw my, so I've got 6 as my parent, right? So it does have a substituent.
So why does some of them put them out, like say like in the homework, where it's got a line in the formula and then a CH3, CH2, whatever?
Well, that would be if you had a situation where you had, let's say, something like this, right? And I was going to put that in a condensed formula, right? That would be CH3, CH2, CH, and then they're showing the CH3 coming off, and then the CH2, CH3. But they also could have just put that in parentheses in the middle, and you would have known that it had to be connected to that one. But sometimes they draw it like that, and that's perfectly fine too.
See, that's what's confusing, is how to know which one's a substituent or not.
Well, if they draw it like this, it's certainly a
Right,
substituent.
that one, yeah, that one for sure I know, but the one up top, I just don't understand how you know.
Well, think about it this way. You know that these are all connected in a line. And you know that these two are connected here. One of those has to be part of the longest chain.
Right.
But you can't have both of them as part of the longest chain, right? I mean, this, you can't go, this is my longest chain.
Right.
It's longest continuous chain, remember? So when you're finding the longest continuous chain, it's about connecting all of the atoms together without raising your pencil. I'd have to raise my pencil and come over here to count that one,
Right.
right?
Okay, so for 423, it asks us to write, it says which alkanes can exist as pairs of easy isomers for each alkane that does draw both isomers.
Of alkanes or alkenes?
Alkenes.
Okay, so
So this is what I got. I just didn't know if I was doing it right or not, and I also didn't know like how to make sure if it was
All right,
only
so-
E or an EN.
remember, the E and Z tell us what?
If they're on the same side or if they're on different sides.
Yeah, but you have to have different things in order for that to be the case. So anytime you have CH2, double bond C, HBr, there is no E or Z. You can't have two of the same group on one of the carbons of the alkene.
Wait, say that again.
You can't have two of the same thing on one of the carbons of the alkene. Right, if I draw this out, there are no E or Z isomers for this. I can't assign a priority to these groups. Hydrogen and hydrogen are identical. Not one doesn't take precedent over the other.
So we say it just doesn't have
It
it?
just doesn't have that stereochemistry.
Okay, yeah, so for that one, I just wrote E, but because I couldn't find a Z because I thought it didn't have it, but I didn't know if we were
E and Z
supposed
does
to-
not exist for
E
this.
does not exist.
Yeah, but now if I change one of them, right, so if I go C.
Well, you can do the second one, CH2, CH, double bond, CHBr. Because I thought this one did have.
You sure that's not supposed to be CH3? I gotta have another bond.
It is not. It's B.
That can't be.
So what's
That's
wrong?
gotta be a CH3. But we can do that one. So, read that to me again, CH3,
CH3, CH, double bond, CHBr.
CH3, H, and then what?
CH3, CH, double bond, CHBr.
Yeah, so this one can have E and Z, right?
Yeah.
So hydrogen is always low, we know that. So this, by definition, has to be high since it's not hydrogen. So this is low, and this is high. And so this is what? As I've drawn it, Z. But I could also draw it like this.
And then that would be, yeah, that's what I thought.
That would be, yeah.
Okay, can you do the last one on there? Because I thought it also didn't have any.
Okay.
Because it had like 3 of the same substituent. So it's like whichever way you put it, you can't really.
Yep, that one can't have it.
Yeah.
Yep. You always have to have at least two, you have to have two different groups on both carbons to have E and Z. If you have one of the carbons that have identical groups, so for example, let's say, what if I did this? Can you figure out whether or not something's E or Z? No, because this group and this group are the same. They're just connected right here, right? So I can't determine E or Z for this particular molecule.
So anytime you have 2 of the same on the same side, then you can't have.
On the
yours-
same carbon.
On the same, I mean, that's what I meant.
Yeah.
But yeah.
Anytime you have two of the same substituents. So for example, if I gave you
Then it couldn't
You can't. You gotta be able to assign high and low on each carbon, and bromine are the same.
But would that have a cis trans?
No. If I draw it the other way, if I switch any two groups, it's the same thing.
It's the same.
And you might not be able to see that as easy on paper, but if you built a model, two models, and you stuck them together, you would see that they're identical.
Can we go over, just, back to nomenclature, just naming a alkene?
An alkene?
Yeah.
Sure.
So with the double bond, just,
Yeah.
with the E and Z as well, just.
All right, so
I'll
let's
take
just,
it all out.
let's just pick on a few things. Let's do this to start with. So what's the very first thing we do when we're naming hydrocarbons?
Figure out the
Identify the.
Figure out the
parent chain.
longest parent chain, and what would that be here? Looks like 5, right? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. But we always want that longest parent chain to contain the alkene. Right, so I'm going to pick this as my parent chain. Right, so there's my parent. And so I know that that's going to be a what? Pentene. E-N-E, right? Now I can number 1, 2, 3, 4, 5, or I can number 1, 2, 3, 4, 5.
Left
You
to
gotta do
right.
one because it's side of the closest.
Yeah, because I want the alkene to have the lowest possible number, right? And so 1, pentene, right? Where's my,
Methyl 2, so 2 methyl.
2-methyl, 1 pentene?
Well, going off of that, can you do this one? This was one of the homework ones. It was a really big one.
Do one that, does that one involve like a chlorine or a bromine, where you have to say like bromo or chloro? I don't know, just like whenever you done one, like Wednesday with iodine, and it was iodo, I would have never
Good.
thought to shorten it to iodo.
I think there's a chart in the book that says if it's like iodine, then it's iodo, it's chlorine.
Yeah, with all the halogens, you just drop the INE, like chlorine, bromine, and just add O.
Right.
Yeah.
So, or is it only gonna be, stuff in those groups and not like, say, like group 1 and 2 with like, sodium or potassium or anything like, is that anything that we would be trying to name like that?
It's only the halogens, right?
Well, the substituents that we've talked about so far are alkyl groups and halogens. That's pretty much what we're going to stick to on this exam. But technically, anything that hangs off of the parent chain is a substituent.
Right.
But we really haven't gotten to alcohols yet. I mean, we've talked about the functional group, but we haven't really talked about naming alcohols yet or anything like that. So I wouldn't hold that name to you.
Right.
Alcohols are a privileged functional group and actually have some special naming. We haven't talked about that. So what's the parent?
Octane.
Octane?
Team.
Octane.
Octene, right? So we're gonna have an octene.
Got it.
All right. Now I can number 1, 2, 3, 4, 5, 6, 7, 8, or I can number 2, 3, 4, 5, 6, 7, 8.
We did 3.
Left.
So it's gonna be a 3, right? All right. So it's going to be, now what do I add?
3 iodo,
3 iodo,
4 methyl.
so 3 iodo, 4 methyl, 3 octene. I got something else I got to do, right?
E.
I got to do E and Z, right? And you think it's E?
I did.
All right, well, let's figure it out, right? So I got a carbon and I got an iodine. Which one's high?
Iodine.
High? Low? All right, here I got a CH3 and I've got a CH2C, so which one's high here?
The CH2.
This one, right?
Yeah, so it's
This
Z.
is high.
You gotta go that far, I don't. That's
So,
what's
okay.
throwing me off, is how far out.
Well, you go out until you find a difference, right? Carbon, carbon. I can't make a decision, right? So what else is attached to this carbon?
Hydrogen,
Only hydrogen, and 3 of them. What else is attached to this?
another carbon.
A carbon and 2 hydrogens. So this takes precedent. Anytime you've got carbons like this, if you have a CH2 and a CH3, the CH2 is always going to be the higher priority. Because it's going to be bound to something that's not hydrogen.
Another car.
Right, another carbon, another whatever, it's
Right.
just not
It still has
hydrogen.
an available bond.
Yeah. And so the highs are on, what's
Z's.
Z?
Same stuff.
On the same side, that's right. Yeah.
Where does that second 3 come from?
That second 3.
Like in the name?
3 octane.
Oh, the 3-octene,
Yeah.
that's telling me where the double bond is.
Okay.
1, 2, 3.
Okay.
That's where the double bond starts. So I know the double bond has to be between carbons 3 and 4. But this carbon also has the iodine on it, so it's iodo.
Did we do anything for naming alkyne?
No,
We just
it-
know that
it-
it's a triple bond?
Yeah,
That
it's just
all-
Y-N-E. I mean, it's the same nomenclature as an alkene, except there is no E or Z for an alkyne, right?
Yeah,
Because
we only
it's-
have one more
yeah, so, yeah.
bond on that side.
That's right, they're actually easier.
Okay.
So if this was